Okay, so last time we were discussing the equilibrium distribution of electrons and holes, right? Electrons go to the conduction band, and holes are left in the valence band, and they are charge carriers, right? So now we want to know, since electrons are fermions, they are free particles, right? So the Fermi-Dirac statistics applies to it, right? And how the levels are occupied is governed by the Fermi-Dirac statistics. Now, in the case of extrinsic semiconductor, when impurities are added to semiconductors, right? Then, as we said in our previous class, that those donors or impurities introduce energy levels in the band gap. Introduce energy levels in the band gap. If we do like a 5-valent, somebody has turned on his speaker very high and mic as well. Please turn off your mic. Please turn off your mics. Okay. So, introduce the donor impurities into it. For example, phosphorus is added to silicon, so it will introduce electrons, extra electrons into the conduction band, or we will say these impurities are called donor impurities, right? And from the energy band diagram point of view, those that it is called doping when we introduce, for example, some impurity into a pure semiconductor. The process is called doping, and this is done during the crystal growth, right? So that doping introduces energy levels in the band gap, right? Now we call them donor states, right? If trivalent, right, is added into, for example, silicon, then that we will call acceptor states, right? Because they introduce energy levels in the band gap close to the valence band, according to the band gap diagram, according to the energy band diagram of semiconductors, right? So how the statistics of those levels which are introduced by the impurity atoms, how are they populated, right, are depopulated? What is the statistics about that, right? So today let us talk about their statistics. Since the particles are particles of electron. So the Fermi-Dirac probability function for donors and acceptors, right? If we represent the density of donor atoms by ND, the density of donor atoms, right? And by small nd, right? If we represent the states those are occupied, right? The states those are occupied by the symbol Nd, the concentration of electrons in the states, right? The states are not yet ionized. Suppose there is not enough thermal energy to ionize those states. Right? If that is conduction band, and this is the energy, bottom energy of the conduction band EC, and this is the valence band, and that is the top of the valence band energy. Right? So if we are talking about donors, donor impurities, right? Right? So we said that energy levels will be introduced by those donor atoms, right, close to the conduction band. And we can call them, as we said in the previous lectures, we can represent them by ED support, right? Okay, so what is the occupation probability, right? What is the occupation probability of those states here, where the concentration of those states, the density is Nd, and this is the occupied states, right? So, if we want to find how many of them are occupied and how many of these states are empty, for example, they have ionized, right? So we would like to find first to apply what is the probability function, right? From Fermi-Dirac statistics, we know that the probability of occupation of any level was equal to 1 over, right? 1 plus e to the power e minus ef over kt, right? The probability of occupation of any energy level, right, by an electron, right, a single energy level by an electron or by a fermion is equal to this thing. This is the probability of occupation of the level, right? Suppose we have and d such levels. So this is, if that is the concentration of electrons, right? Gives you the number of electrons per unit energy per energy level, right? And suppose what will be the total number of electrons? So the total number of electrons will be like you multiply the total states with it, right? Probability of occupation, and you multiply with the total states, right? So I will say the probability of occupation by those electrons, and I turn it into the concentration of electrons of the donor states, right? So how many electrons are there in the donor states, right? There will be like 1 over, which is this thing, plus E, right? And ED minus EF over KT. Now I multiply it with and D, which is the total density of those states, right? That is the probability of occupation of a single state, right? And these are the states, right? So the total number of electrons or fermions, I would say in this case, is this. Remember, here the situation is a little different. There is a slight difference between a simple Fermi-Dirac statistics and the situation in the donor energy levels are accepted as well. There are, for example, look, we will say that each state here is doubly degenerate. For example, you know, the Pauli exclusion principle says that no two electrons can occupy the same state, right? That is the Pauli exclusion principle, right? So, like here, the particles are having an energy state, but they are degenerate by two, right? So one can be spin up and the other can be spin down, like two electrons. Here, however, if it is a situation like this, that is one atom, another atom, and there is a bond, they are bonded to the neighbor atom. And suppose this bond is empty, right? So once an electron sets here, right, and fill in the bond, right? Suppose there is a vacancy, an electron sets there. Although it is two times degenerate, right? Another electron can set there, but the requirement of the bond is complete. The bond does not need any more electrons. Therefore, there is no chance for the second electron to come here, right? So the occupation of this empty state by an electron precludes, it prevents another electron to come here, though there are states, right? Because if this is a spin up electron, a spin down electron can sit there. The Pauli exclusion principle will not prevent that. But here, because of the particular situation, the bond is complete and no second electron is required. Therefore, another electron cannot come here. This limitation or this constraint introduces, right, a factor of 1/2 here. So the Fermi-Dirac statistics, right, or the Fermi probability function is a little different from what it is for simple fermions is compared with here the donor states. The donor states have a little different probability function, and it has this little 1/2 extra in the Fermi-Dirac statistics. You know, this will be the simple Fermi-Dirac, and that is the donor statistics. And this 1/2 comes, and I told you why is it introduced here, because of that constraint. So we say that is because the 2 is because it is doubly degenerate. So generally we say if G is the degeneracy, right, then we write ND, the concentration of electrons, right, in the semiconductor, that will be like 1 plus 1/G, and e to the power ED minus E F over KT, right, and to NT, right? Now, this is the occupied states, the number of states that are occupied, the concentration of occupied states, the states that are occupied by electrons. So we can write that the occupied is equal to the total, what we call is ND, the total, and minus the ionized, right? Minus the ionized, right? So we can write ND like this as well, right? ND is equal to this thing as well. The occupied, right, to the total minus the ionized. Ionized means those atoms, right, are states which have given up, donated an electron to the conduction band, right? When they donate an electron to the conduction band, we call them ionized. And they have been ionized because they have freed an electron. Okay. Similarly, for acceptor impurities, right? If Na is the total density of states, right, of the impurity atoms, the acceptor impurities, for example, a trivalent impurities in silicon, right? And Na is of those that are yet occupied, sorry, not Na, sorry, Pn. Pn is the holes, the concentration of states which are occupied by holes. They have not, they are not yet ionized, right? And Na plus is the ionized hole states that they have given, right? That they have obtained or given an electron to the valence band, right? They have given a hole to the valence band, or they have occupied an electron from the valence band, right? That will be the situation. So in that case, NPA, the whole concentration, right? Similarly, this thing, it will be equal to 1 over, right? 1 plus 1 over G, right? And to e to the power EF minus EA divided by AT into ND, right? Similarly, we can write PA is equal to, right? PA, remember as I said, PA is those states, those whole states, those impurity whole states, right, which are occupied by a whole. Right? So, sorry. So it will be equal to the total Na minus the ionized, right? And ionized here will be R with a negative sign, right? So it's like that is like conduction band, and that's valence band, and these are holes, these, right? That is EA, and that is EV, right? This thing. So a hole ionized means these are holes are here in the valence band, right? So they have occupied an electron from here. So they become negative and negative and negative. Electrons, uh, or we can say that electron jumps to the bed, occupied bed level. Then we can say a hole is produced, right? And it will be like you can say that these right, these are now negatively charged, right? The acceptor states get an electron from here, so we call them negatively charged, right? And they are now ionized holes, ionized layers, right? Okay, now this is the statistics for holes and sorry, the statistics for impurity states if they are donors, right? How those states are occupied, right? These are the states. In case of trivalent impurities, for example, you put right uh, aluminum, right? So into silicon, so that will be the situation, right? And these are the energy levels introduced by those acceptor impurities, right? So, what is the probability of occupation of this state by an electron? And what is right? How can we write them in terms of the ionized impurities, total impurities, minus ionized? Some have obtained right an electron from the valence band, so they have become ionized, right? So the statistics or transport of electrons in the semiconductor will be influenced by these situations, right? Now let us see that what happens at ordinary temperature, how many of those are ionized. Suppose we have donor states introduced into the band gap. So at any temperature, what is the situation that those states will be occupied by an electron, or if they will be ionized because of the thermal energy available to them, right? So let us discuss an other term which we call it complete ionization, right? And freeze out. So let us see what is a complete ionization or a freeze out. Complete ionization. Right? Suppose, for example, we have that is the conduction band, and that is the valence band, right? That is the intrinsic Fermi level, EFI, intrinsic Fermi level, right? So donor states are somewhere here, suppose ED, right? These are donor states. So if there is enough thermal energy, these states can donate an electron to the conduction band. They can donate an electron to the conduction band. And in that case, we will say that the this state, this donor state, is now ionized because it has given an electron to the conduction band. We call them as ionized. And if all of them donate electrons to the conduction band, we will call this as complete ionization. Right? We will call it complete ionization. Now, from the Fermi-Dirac function for the donor states, right, are the probability of occupation of donor states, right, or the total number of, or the concentration of, or the density of the occupied states, right? We write them as ND, right, is equal to ND by 1 plus 1 over 2, right, e to the power ED minus EF over KT, right? If we say that ED minus EF is very, very greater than KT, if we assume this, then we can estimate this by Maxwell Boltzmann distribution function. You can neglect one, we have done that, right? So MG, the concentration of, or the density of occupied levels, that will be equal to ND, which is the total states, right? And 1 over 2 e to the power, we neglect one then, ED minus EF over KT, right? We will say ND, right, is equal to 2 ND e to the power minus ED minus EF over KT. That is the concentration of occupied levels, right? So if ED minus EF, right? If ED minus EF is very, very greater than KT, then we can say that EC minus EF will also be very, very greater than KT, or we can write the intrinsic electrons concentration, right? The electrons are under equilibrium, right? And if they are intrinsic, then N0, which we call the intrinsic carriers, that was equal to, if you remember, NC from the previous topics, right? And e to the power minus EC minus EF for KT. That is from our previous work. We have done this. So that is the concentration of intrinsic carriers, right, in the conduction band. This is the concentration of electrons in the conduction band, right? So now we are interested in, right? We will be interested in how much of them, right? This, how much of them are occupied, how much have gone to ionization, right? So we would like to find the ratio between, right? What is the ratio of the occupied to the total, right? Some are ionized. So what is the ratio of occupied? So we want to find the ratio of those that are ionized, right? And those, right? They are, for example, anode. Some have gone with, some have donated electrons, right? Free electrons to the conduction band. So the ratio of the occupied will be equal to ND divided by, right? Divided by the ND plus N naught. That is the total. That is occupied. And that is occupied plus the number of electrons, or we can say the ionized, right? So there is the total number of all the states, we can say, and then those they are occupied. So we have to find this ratio, right? What is the ratio? We have to find it. How many of them are still occupied? So we will find this ratio, all right? So let us write ND from here, right? So that will be equal to ND 2 ND e to the power minus ED minus EF over KT divided by ND. So again, this thing e to the power minus ED minus EF over KT plus N naught, which is the number of free electrons, right? And it was equal to this thing, right? So there will be NC e to the power minus E minus F, EC minus EF over ET, right? So now let us take this is common from the denominator. This, let us take this as common, right? So 2ND e to the power minus ED minus EF over KT, right? Divided by, take this common, so 2ND e to the power minus ED minus EF over KT, and to 1 plus, right? When we take this common, it will be NC over 2ND, right? E to the power minus EC minus EC. Right? I take this thing common from the denominator, or I give this thing, right? So this goes with this. Now the ratio ND over ND plus N naught is equal to 1 over 1 plus NC over 2 ND e to the power minus EC minus EF over EC minus ED. EF is gone here. When you take this common, the EF cancel. There is EF here, there is EF there. So let that is equation number whatever. This is the ratio, right? The ratio of those that are still occupied, the ratio of the states occupied to the total, right? And this is equal to the exponential, 1 over exponential term, right? So we see that EC minus ED, that is the ionization energy. Ionization energy. EC, that is EC, and then is E minus ED. This like this area, right? So EC minus ED, that is the ionization energy, the energy required to ionize this donor states. Right? So if we, as we said, right, that it is, if you remember, we said that it was equal to 25 millielectron volt, right? That is the room temperature energy, and we said that this ionization energy is equal to kind of that. So EC minus ED is nearly equal to KT, the room temperature energy, right? And we know that this NC is very, very greater than ND. This ND is the donor concentration, and NC are the effective density of states, right? Effective density of states in the intrinsic semiconductor. So this is a very large number as compared with ND. So NC over ND that is very, very greater than 1. That is very, very greater than 1, right? I can say that NC is very, very greater than 1. So when this is very, very greater than 1, right, this thing is very, very greater than 1. So this whole thing is very, very small. If this, we know that NC is very, very, at room temperature, we said the ionization energy is nearly equal to KT, which is the room temperature, right? So at room temperature, this is the situation, this is equal to e to the power 0, which is kind of 1. E to the power 0, which is kind of 1, right? Or e to the power 1 or whatever, right? Not 0, but 1, e to the power minus 1, 1 over e. Anyway, that is a constant factor multiplied by this. But this is a very large number. When this is very large, this makes this very small. So here, what we did is what we did, this is very, very large. So ND, sorry, that is small n, ND or ND plus N naught, that is very, very small than 1. The ratio of, right? The ratio of the occupied to the total is very, very small at room temperature. So the density of states are those states, those donor states. The probability of occupation of them at room temperature is very small. So it means that they are all ionized. So it means that they have all given an electron to the conduction band to be free for conducting electricity, right? So at room temperature, it is behaving like a conductor because the probability of occupation, the ratio of the occupied states to the total states is very, very small. We can see, and D is very, very small, and D plus and naught, which is the total, right? So the occupied concentration of the states, that is very, very small. So this situation, right, is called complete ionization. Complete ionization. They have given an electron to the conduction band, right? Or have given EC, that is EG, and that is EFI, intrinsic, that is EV, so at room temperature, they have given electrons. So they are all almost, they have given electron to the conduction band, and they are ionized now. These donor states are ionized now. So this situation is called complete ionization. At room temperatures, those donor states are completely ionized and they provide uh, electrons to the conduction band for the semiconductor to conduct electricity. Right? You can to estimate how much of the donor states are occupied still at room temperature. For that, to get an estimate, you can do example number 4.7. To get an estimate how much, how many of the density, how many of the donor levels are still occupied, right? And they have not yet ionized at room temperature, right? Now we said there is another phenomenon. We will call it a complete freeze out, right? Freeze out. Freeze out. Suppose we take T is equal to, suppose we are at 0 Kelvin, right? Hmm? So suppose we are at 0 Kelvin, right? So we say at 0 Kelvin, all the donor states will be occupied, right? The donor states will be occupied. They will not be ionized because there is no energy for them to get. You know, these are the donor states. These are the donor states. So and T is equal to 0, those donor states will not be ionized because the semiconductor does not have enough energy so that the donor states could donate an electron to the conduction band. So they will be occupied. So in that case, and the occupied will be equal to the total. The occupied will be equal to the total, right? We will say that and the ratio of the occupied to the total, right? That will be equal to 1 over 1 plus 1 over 2e to the power ed minus ef for kt, right? I will say, since this is equal to this, therefore this ratio is equal to what? This ratio is equal to 1 because they are equal. Right? So the occupied ratio of the occupied to the total is equal to 1. And when we put the equation here, we get this thing. When that is equal to 1, well, we see that this is equal to 0, right? If this thing is equal to 1, this must be equal to 0, right? At is equal to 0 Kelvin, right? And this that means that Eg minus Ef, right, over Kt should tend to minus infinity, right? And for that situation, if this is the situation, we see that Ef is greater than E the donor level, right? EF should be lying somewhere here. The Fermi energy in this situation, we know that the Fermi energy, right, is a function of temperature. If I can give you like you can go to Wikipedia and see how the Fermi-Dirac function moves with temperature. It moves with temperature. So it changes with temperature, right? So here, the Fermi level at complete freeze out must be above the donor level so that at 0, T is equal to 0 K, all the donors are occupied. We said that Fermi level is a level below which all the right particles states are occupied, right? The probability function below which is equal to 1, right? So here the Fermi level will be this at complete freeze out. At complete freeze out, the Fermi level will be above the donor level, right? So these are the concepts, a few parameters or concepts in semiconductors, and impurity semiconductors are extrinsic semiconductor, like the complete ionization and the freeze out. Now we go to another topic in semiconductor, right? And that is compensated semiconductor, right? When there are donor levels, right? When there are donor impurities, as well as there are acceptor impurities. Those kind of semiconductors, they are called compensated semiconductors. Right? For example, an N-type semiconductor we have, and we also have their P-type impurities. So that type of semiconductor is called a compensated semiconductor when they have donor impurities at the same time when they have acceptor impurities. These kind of semiconductors are sometimes useful in fast switching devices because the compensation actually it can increase the chances of recombination of the carriers. Right? Let us see what is meant by that, right? I will say we want to calculate electron in the conduction. Then I want in a compensated semiconductor, I want to calculate the number of electrons. So there is a famous condition which must be obeyed. The charge neutrality condition, right? In order to calculate the number of electrons in the conduction band, we take help from the charge neutrality condition. Right? The charge neutrality condition means that at thermal equilibrium, right? When there is thermal equilibrium, the positive charge must be equal to the negative charges. Because when you dope a semiconductor, you are not introducing an ion into it. You are introducing a neutral atom into it. And a neutral atom does not change the ratio of already charges over there. A semiconductor is actually neutral. It does not have any charge. So when you are introducing impurities into it, either if it is whole trivalent impurities like donor impurities or acceptor impurity, it does not make any difference. It should be neutral, right? So